All right, hey everyone. I will get started here. I'm going to be talking about horizontal scaling for L2s. This applies for all L2s, even though I work at Tyco and this is what we're focusing on. But this idea is something that's really to be enabling horizontal scale for all L2s. I lead the DevRel team at Tyco, and let's get right into it. So today's agenda is we'll start out briefly. I think this is a more advanced audience, but we'll briefly go over what the scaling problem is. Then we'll talk about all the cool scaling ideas that everyone is kind of working on now at current day. Then we'll be talking about new precompiles. So these precompiles I actually just recently suggested as a roll-up improvement proposal. I'm not sure if you've been following like the RIPs / roll call calls, but I recently just proposed this there. And then we're going to be talking about something very cool that we're working on at Tyco called booster roll-ups. We'll be talking about this singularity thing. All right, so the way that I like to frame this scaling problem in a really simple way is that if we want people to be using Ethereum, it would look almost like a world where we want people to be able to drive to all different places around the world, right? Like they're able to go from A to B, C to D. These are like the state transitions. And if we want this world where everybody's driving their cars all over the place, it's this great, beautiful city, then we're going to need a lot of gas. And one of the problems that people have for scaling today is that Ethereum happens to bound the supply of gas. So no matter how much people want to run around the world, drive their cars everywhere, use this beautiful network that we've built, they just can't. There's a limited supply. And that limited supply is 15 million gas every 12 seconds. It can adjust a little bit because of EIP 1559, but eventually the target will come down to about 15 million gas per every 12 seconds. This is what we keep it at. So we can say, all right, like, how do we want to improve Ethereum scale, right? So this talk is about horizontal scaling, but we'll briefly talk about vertically scaling as well. You know, one thing you can do is you can make cars go twice as fast, right? If you make the single thread performance of the EVM go faster, then you're able to do more eventually. Additionally, you could just add additional threads. This is like adding additional lanes. But even if we were able to achieve these kinds of things, and even computers now might be fine at processing this type of throughput, we still would bound the gas supply if we didn't also double the efficiency of the storage, right, of the node. Because really we're bounding the gas supply to rate limit the state growth for nodes, right? Another way to put this is for scaling, we want to do more with what we currently already have, like this kind of 15 million gas or so. So we want to be able to do more scale without raising the barrier of entry to consensus, without raising the requirements for running a node. Okay, so what are some of the current scaling ideas? So one is you make the data availability cheaper. So you can use things like validiums. You can use alternate DA layers. Another thing is like you can do the sharding, the data availability sampling. You can offer different routes for data, which we're doing with like blob storage. And yeah, so that's the cheaper DA stuff. The other cool thing that you guys, I'm sure you've heard a lot of the teams doing, like at Optimism, Polygon, ZK Sync, is everybody's kind of working on this idea of creating some type of super chain or hypernet where you have we recognize the issue of a single thread because each rollup is still, at the end of the day, a single thread that needs to process a certain amount of transactions within the block time, and that you're going to need more threads. So we know that we need more than one rollup, right? So what a lot of these teams are kind of coming up with is like, okay, let's have a bunch of L2s in parallel, and let's have them all like share a bridge and make them be like very composable. And this has a lot of pros. Those are kind of the pros. It's horizontally scalable. These L2s are composable. They share the same security. So all of the dapps inside of these ecosystems work kind of nicely. But there are two cons that we're going to try to address in this talk and with this improvement proposal. is there's still fragmentation between these like superchains or like hypernets and things like that. And developers still need to take their application and deploy it on an L2, at least one of these, right? So the question is, for L2s, can we skip the copy-paste deploy? Can we somehow scale Ethereum without requiring developers to deploy to a rollup? Is there a way to just make Ethereum itself scalable and kind of just shard the execution and storage of the L2s? So intro to 3 new precompiles that open up a design space for an idea that will allow us to get this kind of scale for Ethereum without with developers not needing to deploy to L2s. So these are the 3 precompiles. The first one is the L1 sandbox call. So this, these precompiles all take advantage of the fact that we know L2 nodes need to be running the node, the node which they're downloading the rollup data from, right? So we know L2 nodes are running L1 nodes, like they have to be. Or maybe they're not running it, but they need to have access to it over an RPC to be able to fetch from the DA layer and build the rollup state. So these precompiles take advantage of that fact. Yeah, the first one is the L1 sandbox call. It's super simple. From L2, you call this precompile, and you get to like read and write L1 state. It's similar to a static call, except the transaction won't revert if you do like a write. It'll just discard the changes at the end of the precompile. And the second one is the L1 delegate call. This one executes a smart contract like stored in L1, but it uses the storage of the L2. And then the L1 call allows you to read and write L1 state on the L2 and apply all of the storage slot updates in one go. And we'll take a look at some examples to make this a lot clearer. Okay, so let's look at this simple example on the left. This is the L1 sandbox call precompile. So at the top, we have a very simple contract. It's just a count with an increment function that increments that count by 1. And on the bottom, we have an L2 contract, which simply does the sandbox call and calls this increment function. We can see here in the first require statement that we're asserting that the L1 contract, the return from this precompile is a value of 1. So it incremented the state on that L1 contract. And you can see in the second require that the state changes are discarded at the end of the precompile. In the second example, you can see where we're using the L1 delegate call. The L1 delegate call, as you can see in the first require statement, that it calls increment, but it returns a value of 11. The reason why it returns a value of 11 is because it's using the storage of the calling contract. It's using the storage of the L2. So we can see it gets 11 there. And in the second require, we call count, and then we can see that the state changes are persisted. And the last one, this is kind of like a little bit of a spicier one, but this is the L1 call. This is kind of using a ZK EVM as a coprocessor and a bit of a extreme usage of these precompiles. But the way that it works is you essentially do these state changes on the L2, and the node keeps track. For each contract address, the key is like a tuple of the contract address in the storage slot. If the storage slot hasn't been touched yet, it'll add it to a list. Otherwise, it'll update the value in the list. And as it does these, it'll batch all of the changes and apply all of them inside of one write back to the L1. So you're kind of batching these changes, and it's kind of like a stateless thing, but we do need to keep track of some state, which I'll share some links at the very end of this slide because this is a bit dense, and yeah, but it's not fully stateless, but almost there. Okay, so this is the thing that I tried to lure people into, the idea of the booster rollups. When I was originally saying, is it possible to scale L1 directly and not require developers to deploy to L2s at all? And that's basically the idea of a booster rollup. So a booster rollup essentially deploys a proxy contract. This wouldn't actually be a contract because that would change like the gas costs. It would be like implemented in the client. But for example's sake, each account would have a proxy deployed to it. And this proxy would just delegate calls to the L1 node, which the L2 client already has access to. And yeah, it'll check the L1 contracts can optionally implement an interface, making some of their functions parallelizable, right? So what's an example of something we can do in parallel? We can do, for like a token contract, we can do transfers in parallel. And one thing that we can't do in parallel is like something like getting the total balance. So this would slightly augment the experience where developers kind of suddenly get this multi-threaded environment where they can shard their storage and execution and optionally implement this kind of interface. So yeah, another way to think of this is booster rollups perfectly mirror the L1 and just shard the storage and execution of them. Yeah, and another interesting thing about this and why I kind of prepended this as well is that this is not just useful for Tycho, but really hopefully useful for all kinds of rollups, is you don't have to do a booster rollup. You can still take advantage of these precompiles. You can read like Oracle data on L1, or on your rollup, which doesn't do this by default for every single dApp, you can boost some of your dApps. Yeah, and then this is the official cover image of booster rollups. This is like how Ethereum endgame scaling looks like in a picture. But yeah, this is a bit dense, and I can answer some questions after, and I have some resources. But the basic idea is this. So Tycho works we're building a based rollup. That means that we don't have a centralized sequencer. We just use the shared sequencer of Ethereum, the L1 validator set. And the idea is you can take booster rollups and combine it with a based rollup. And these rollups can share validity because they have a shared sequencer by nature of being based. And with this shared sequencer, you can kind of have atomic synchronous transactions between all of the L2s inside of this booster rollup network. And everything kind of looks like a single chain. So yeah, that is the basic talk. So at the very top, right here on the right, I have a QR code in case you want access to any of these links and you want to read more about any of the topics that I went through today. The first one is a roll-up improvement proposal, which I posted in the Roll Call Telegram group if you're a part of that, and would really love your feedback just to hear like what you think of it. Is there any glaring issues? Do you think this is useful for all L2s in the ecosystem in general that we can implement for clients? The second one is about this shared validity sequencing from Umbra Research. This is how optimistic rollups and how we're inspired for our based rollups to achieve these atomic synchronous transactions. Then we have the ETH research posts on booster rollups, another post on multi-layer dApps, ZK sharding by nil, which is another interesting approach, which is kind of very similar to this, and we'll be having like some Twitter spaces and talks about this with them as well. And yeah, this is my Telegram. So I think I have time for questions, and yeah, thanks.
David afterwards. Okay.